From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez.
A high volume die cast part will cost you about $10 a kilo. That's when you get into the automotive sector. Sand cast parts around that $50 to $100 a kilo. So 3D printing was, a factor of 10 or a factor of 50 beyond what is typical in the industry today. And so that was really the challenge that we set ourselves is could we take the cost, and that then comes down to speed, of course, because manufacturing speed's everything. And take that from, the $1,000 to $5,000 a kilo we're paying today for metal and get it into that $50 to $100 block. And to do that, there's numerous things you have to do. Now, the first one and the most important one is speed, and that's the name of the company. You do need to be able to produce parts fast. And typical, give you some real numbers here. So a typical laser bed, you're looking at, 0.1 to 1 gram a minute. And then you can do your math about how long your part's going to take. Really, you need to be up into that, 10 to 100 grams a minute. If you're not there, you're not manufacturing, you're really just building expensive prototypes. So we looked at that, and that's just a physics equation. It's not difficult. In a typical melting process, you have to take a solid to a liquid and then back to a solid, and that takes time. And you can work out that time, and that's very easy. And then you work out, right, with a traditional melting process, you just come up against a speed limit, and you can't fix that. So how do you then fix that? Is you don't melt the powders.
That was Byron Kennedy. Byron is the co-founder and CEO of SPEE3D, a high-speed metal 3D printing company. He is a serial entrepreneur, having co-founded the first spin-off company from Charles Darwin University before exiting to the New York Stock Exchange listed company Regal Beloit. His current company, SPEE3D, has developed a new 3D printing process for metals, supersonic 3D deposition. Targeting commercial and industrial applications, the technology is suitable for a vast array of materials, including copper, aluminum, and other metals. He joins the show to talk about SPEE3D and approaches to increase the throughput of 3D printing metal. Byron, do you want to just get started with introducing SPEE3D to the audience?
Yeah, I'll start with an introduction on myself and the company. So SPEE3D is a manufacturer of metal 3D printers based in Melbourne in Australia. And the technology is quite unique in that the process that we use is based on cold spray. So how that actually works is inside our printers we have a small rocket nozzle, and we use that to accelerate air up to about 1,000 meters a second. And what we do is we then inject metal powders into this high speed air. And of course, those metal powders then get accelerated up to very, very high speeds. And when they hit a surface, they then stick and then create these full density parts. And this process was known as cold spray. It's been around for 10, 20 years and used in the repair world. So for instance, if you have it's used a lot by the military in repairing things like helicopters and tanks. So if you have a corroded part, and these are very expensive parts in the military, let's say it's a $100,000 part and it's got some pitting corrosion, cold spray is being used to then fill that hole due to the corrosion, and then you machine it back. So what we did is took a repair technology and added very sophisticated software to be able to turn a coating process into a manufacturing process. And that's really where the company was born and where we came about from.
And can you talk about kind of your kind of venture into additive manufacturing? I know reading a little bit about your bio, you started with this not your first company. So how did you kind of target cold spray as technology to invest your time and resource in?
Yeah, no, great question. So the history actually goes back before this company. So I'm one of the founders of SPEE3D as well as Steve. And previously we had another company which was designing and building electric motors. And these motors are used in things like pool pumps, in air conditioners, electric bikes, and those sorts of applications. So we built that company and we sold that company to a large US manufacturer called Regal Beloit. And that was very successful. And we set up production lines for those electric motors in Thailand, in Mexico, all around the world. And we're exporting that motor globally. During that process, we spent a lot of time developing new motors and variants of that existing motor. And we always came across the challenge about how do you get cast parts fast and economically and cheaply and with being able to iterate around the designs. So in the world of production, you typically build a first prototype, then you'll build 30, then you'll build 100, and then you'll get into mass production. So how do you work your way up through that? And traditionally, to cast a part, you have to make tools, and you're looking at about a 12 to 16 week lead time for tools. So we're very aware of this issue of casting slowing down the development cycle of traditional components like electric motors. So when we finished up at Regal, we knew of 3D printing. We'd used it a little bit in that company, but the challenge with 3D printing was that it was just too expensive and too slow. So a typical laser-based technology will cost you between $1,000 to $5,000 a kilogram for a part. So fine if you're making a one-off prototype, fine if you're making medical, fine if you're in the aerospace sector, but certainly not fine for production of parts in commodity manufacturing. So to give you a realistic number, a high volume die cast part will cost you about $10 a kilo. That's when you get into the automotive sector. Sand cast parts around that $50 to $100 a kilo. So 3D printing was, a factor of 10 or a factor of 50 beyond what is typical in industry today. And so that was really the challenge that we set ourselves, is could we take the cost, and that then comes down to speed, of course, because manufacturing speed's everything, and take that from the $1,000 to $5,000 a kilo we're paying today for metal and get it into that $50 to $100 block. And to do that, there's numerous things you have to do. Now, the first one and the most important one is speed, and that's the name of the company. You do need to be able to produce parts fast. And typical, give you some real numbers here. So a typical laser bed, you're looking at 0.1 to 1 gram a minute, and then you can do your math about how long your part's going to take. Really, you need to be up into that 10 to 100 grams a minute. If you're not there, you're not manufacturing. You're really just building expensive prototypes. So we looked at that, and that's just a physics equation. It's not difficult. In a typical melting process, you have to take a solid to a liquid and then back to a solid, and that takes time. And you can work out that time, and that's very easy. And then you work out, right, with a traditional melting process, you just come up against a speed limit, and you can't fix that. So how do you then fix that? Is you don't melt the powders. And so we were looking for a process that wouldn't melt the powders. We fortuitously came across this process called cold spray. We looked at it. We saw what they were doing in the military. We knew we had to adopt it, because you can't just take it as it is and then expect it to work. So we then did the engineering, and in particular the software development, to be able to take a coating technology and turn it into a manufacturing. But really the key is identifying that unless you speed up the process, your economics aren't going to be favourable. So that was really what led us into the cold spray world.
And when you think of speed, do you think of it just in the context of how fast you can build a part up, or the entire workflow with kind of setting up a build plate or kind of post-processing, all the back end stuff as well?
Absolutely both. Firstly, you do have to start with a full understanding of that supply chain. And if you see some of the videos of our printer, you look at it and you think, wow, that's upside down. So what we actually do is we have the nozzle on the bottom of the printer and we're firing the metal powders upwards. And essentially that's getting the powder is depositing on a plate on the end of a robot arm, which is then doing a dance around the nozzle. So typically people have done it the other way. They put nozzles on the end of robot arms and then they've had the parts stationary. So why did we invert the whole process? And that's an understanding of the supply chain. So if you want to get into manufacturing, you need to be able to understand that whole workflow. So what happens is if you build the part on the end of a robot arm, you can then build one part and that robot can then automatically eject that part onto a tray or into another robot, which will then go directly into a CNC machine, which will then be finished. And if you have that vision from day one that you need this to be an automated process, that is what needs to be done. You know, I do see a lot of challenges around the traditional powder bed system is you're making 100 or 1,000 parts on a tray, then you've got to somehow manually get those parts out of a tray. You've got to get rid of all of that powder. And that's not an automated process. So if you go back to traditional manufacturing and you look at the Toyota production system, they always talk about single piece flow. And what single piece flow is making one part, not batch production. And there's various reasons for that, which I can go into or we don't need to. But the advantage, there's significant advantage of making single parts one after another rather than batch production. So if you take all of that together, that's why we design the printer in this upside down manner, such that we can produce one part and then push that off and then produce the same part again, or a different part, doesn't make any difference, but it's producing one part at a time. Now, it's not to say the technology can't make multiple parts, we can at the same time, but traditional manufacturing dictates that single piece flow is the most cost-effective way to do that. And then on top of that, of course, the printing technology has to be fast, and you have to be able to produce it so at a speed. So we're working on a project at the moment where we're producing parts in about 4 minutes, and then the post machining is about 5 minutes. So we're able to produce parts now quicker than the post machining, and that's about the same time. And that's the ideal scenario for manufacturing, is to produce a part and then make sure that the processes that follow are of a similar time frame. If you can do that, then you can produce just-in-time components and all of the lean principles that are taught in manufacturing.
Right, and I think the thing that really emphasizes this for me when I was first reading about you guys and seeing you at trade shows was that I can't remember if it was Formnext or Rapid last time I saw the machine, but you were making kind of hammers and actually like having them on sale at your booth and actually showing like, hey, we're making these all during the show, like people are buying them, but we can replenish it. So like I really like that approach, saying, hey, like this is production, we're doing this here in this funky warehouse trade show area, and think about potential if you have a real setup. So I like that mentality of thinking through the process in the fact that it's production. You're not necessarily hamstrung by conventional thinking of other technologies that may have come previously.
Yeah, 100%. And then that's really the vision of being able to show that at a trade show is, in a booth, or, at an event, we can bring in a machine. It takes about 2 to 3 hours to set up. Then we bring in a CNC machine, and we can have the full production line running at the trade show. and really it takes about a day to set everything up and get it running. But being able to do that in a production environment, of course, very, very simple. It's small, it's compact, and really it's about being able to produce a lot of material. So just to give you an example, we can produce about on any of our machines about 25 tonne, say it's copper because we do a lot of work in copper at the moment, 25 tonne of material. So that's about 50,000 pounds of material for a printer per year. Roughly 250 kilograms per day we'll be able to put out. And just to give you an example as a comparison, a typical SLM machine will produce about 250 kilos in a year. So we'll be producing the same in a day what a typical laser machine will produce in a year. And that's what you need to do to be able to really hit the production markets. You can put, for one of our machines, you can put 365 SLM machines in parallel and you'll have the same output. So that's the order of magnitude increase that you need to do to really hit the production markets.
And so when you're talking to customers about your technology, kind of what do you think of as in terms of sweet spots for applications? Is it a material consideration that if they're looking for copper, or are they looking for other materials, or is it particular design or geometries, big parts, small parts? Is there something that kind of resonates with the customer base?
Yeah, I'd say it's at the moment it's 50-50 in terms of two applications which are really high level applications, which I'm talking here, which are really seeing the most benefit. One's in defence, which I'll talk about in a moment, and then the other is in high volume production of parts around the copper space, because we can print copper and aluminium very, very simply, but copper's a really difficult material to traditionally work with, and this is not just in 3D printing, but in manufacturing as well. So it's a difficult material to cast, it's a difficult material to machine, but it's a high volume material. So if you look at the world of metals, there's three metals in the world essentially. There's steel, there's aluminium, and there's copper, and everything else is a distant fourth. So in terms of the copper materials, it's very, very easy for us to make copper and the various alloys out there. So we do copper chromes, copper tungstens, copper chrome zirconium, all different styles of copper for different applications. And they're used in lots and lots of areas, such as electrical distribution. They're used a lot in the military, even aerospace use copper materials. So we are seeing a big interest around those high volume copper applications because we can produce copper so quickly. And then the second is defence, and I can chat more about defence, or we can continue on that. So
yeah, let's go into that application specifically.
Yeah, so let me now talk more on the defence sector. Now, defence have interesting requirements in that they need parts very, very quickly. And when we're talking quickly, we're talking in a matter of hours. So if you're on the front line and one of your vehicles or vessels break, you need to then fix that. And you need to fix that and get it back to base as quickly as you can. And the challenge with the Defence Force is supply chain. So when Defence Forces are at remote locations, how do they support their frontline troops? And this is what we call expeditionary 3D printing. So this is printing on or near the front line. So it could be on the front line, or it could be at a forward supply base. So either of those we classify as expeditionary 3D printing. So the key to expeditionary 3D printing, as I alluded to, is speed. And you need to be able to print parts in a matter of hours. You need to get them out there into the field, and you need to fix those vehicles or vessels or whatever the requirements are. And so we've done a lot of work over the last year with the Australian Army to prove this out. And what we've done with the Australian Army is actually put printers onto the back of their military vehicles or vessels and taken them into the field. And literally it's driving it into the middle of the bush. And we've done multiple exercises now in conjunction with the military to take them into the middle of the bush. We have the printer, and then we have all the accessories that go with it. So heat treating furnaces, CNC machines, the various accessories to run the printer, generators, computers, everything. And it's a matter of then setting this up, and we can set it up very, very quickly. So typically pulling it off the back of a truck, we can be up and operational within about an hour, and then and then printing parts in the middle of the bush. And certainly, you know, traditional laser bed machines would never cope with even, you know, transportation on the back of some of these trucks that we deliver these printers on. So the beauty about this technology, it's very, very robust. It's made with very industrial equipment. You know, there's no high precision optics or leveling required or any of those sorts of things. So we drop it in the middle of the bush, and when they drop them, they drop them hard. And then you know, we're printing either aluminium or aluminium bronze, like various materials in the middle of the bush. And really, defence is a fantastic consumer of parts, because the parts could be anything. You know, they go from anything from brackets and steps to pulleys and you know, whatever breaks in the field is really the requirements of the Defence Force. So so expeditionary is a key market for us and for 3D printing in general going forward. And really it's about, you know, you need to be able to prove that you can drop these printers wherever you need to, and you need to be able to use them, and it needs to be able to be used by a soldier or a sailor who's trained, of course, but it certainly can't be a PhD in a lab. You know, these are real world environments we're working on.
Do you have specific design approaches or design constraints when you're working with these teams in terms of conventional laser bed has support materials, and you have to think about shrinkage and warpage and all that? Are there specific design for AM approaches with your technology?
Yeah, every technology is the same, of course, in terms of you know, requirements and design guidelines and those sorts of things, and that's from, you know, AM through traditional subtractive manufacturing and casting as well. So no difference there. We have, you know, a series of constraints which we need to work in. You know, we can build very big parts with this machine. So our expeditionary machine, for instance, can build parts up to around about 100 pounds and about 3 foot by 2 foot roughly. So you can build very, very big parts. You know, typical in these applications, you know, we're seeing parts that are built in an hour or two and then getting them into the field. So yeah, certainly there are those requirements. You know, we have sophisticated software, as I've talked about, which is used on the machine to generate the robot tool paths which we need to build those parts.
And then your process is not an inert, doesn't require any inert atmosphere, is that right?
No, and that's one of the reasons we can do this in the expeditionary environment. So we just used compressed air. So with the printer, you need a compressor. But that's the beauty about this, and you know, if you can take a compressor out to site with a military application, which is very, very simple, then you can run the printer. But this is also relevant for other heavy industrial applications. So the kind of applications that we're talking about there are mining, oil and gas, rail, and those sorts of applications where you need parts very, very quickly, or, you know, to fix a particular problem that you've got. So, in Australia, we have a lot of mining, and the mine sites are at very, very remote locations, and getting parts to those remote locations take time. As an example, the production lines at the mine sites, if they go down, they cost in the order of $2 million per hour. So to stop that happening, they have a very large stock of spare parts, and 3D printing has the ability to be able to help with that and really to eliminate those big stockpiles. And you of course the parts need to be used in the right way, and they need to be the right style of parts. And that's just based on the technology that's chosen.
And can you talk about how your materials differ kind of on the powder front from a typical laser-based process? Are you talking about kind of similar particle size distributions, or are you bigger or smaller than the conventional powder bed systems?
Yeah. So the process, as I alluded to, called cold spray. So we're spraying these metal powders. The advantage of spraying these metal powders is we can handle pretty much any shape. So we don't like flat plates, but other than that, potato shapes are fine. Spherical, actually, interestingly, is not a big advantage to us, because the best shape is actually a potato shape, because they fly the best in the airstream. Now, the beauty about the potato shaped powders is they're much cheaper than a spherical powder. So this is another reason we can push the cost down, because we can use a lower cost process to manufacture the powders. So as an example, in copper, we can use water atomized coppers rather than gas atomized. And these powders are therefore a lot cheaper, and you're getting into the commodity pricings that you can buy powdered metals for. So it always is interesting to me the price that some of the powders are sold for in the 3D printing world compared to a traditional commodity metal powder. Commodity metal powders are a fraction of the price that is currently being used in the 3D printing world. Now, there's some good reasons for that, but certainly you can see where the price can get to when 3D printing can use commodity powders over the very specialized powders that are used today.
And so as you've kind of grown the company and started to get visibility in various industries, from defense, oil and gas, and others, what do you see as some of the challenges and the conversations as you have with people who have different types of metal 3D printing kind of in mind as their default? Are there challenges that you have in explaining how yours works, how yours is different, or the advantages or challenges?
Yeah. So the world of metal 3D printing, of course, there's many technologies out there today, and it's a bit of a minefield for customers. So traditional metal printing is the default is laser-based technology, of course, and really, laser have done a very good job over the last 10 years of convincing people that 3D printed parts have to be expensive and very, very complex. There's this fallacy which says, complexity is free. Well, no, complexity costs $1,000 a kilogram. So that is that's where people's mindset is traditional. Is I need to make something extremely complex to make it viable on 3D printing, and that is the case if you're using traditional metal printers. So what we've done differently is to have to educate people that no, we can actually produce parts at $50 to $100 a kilo, which is in line with cast parts. So you can use a very traditional style part and be able to produce it at a cost which you are very familiar with today. And that's a mindset shift for the 3D printing industry. And look, it is taking some time to get that through. We've employed some great leaders across the world, in the US with Bruce Coulter and Paul Holoardi, and also Stefan Ritz in Germany, are leading up our sales operations in those two regions. And it's about, really educating the market that 3D printing can be economical. You do need to still do some design to make it, optimized for the process. But, we can show to people, look, here's how much it costs to run the machine, and here's how much it will cost in production for these particular parts.
And do you still see a typical model with kind of even across the board with different 3D printing technologies as machine manufacturers, you are part selling machines, but also part doing a lot of development and almost internal service bureau model or work for customers? Is that a typical pathway for customers who are interested in the technology, may not want to buy right away, and you guys do some development work with them and kind of take them along that journey of discovering the technology?
Yeah, that's pretty much right. We're happy to build some parts for customers. Ideally, we will then push them out into the service bureaus that have our printers. Our business model is really selling the printers. And what we've done now is also move to a model where people could try it for a year, essentially lease the printer office for a year, give it a go, see if it works for their particular application or idea, and really it's a try before you buy model. We're happy to do those sorts of things for customers because this is a new technology, and 3D printing is new as well. I do think that over the last year or two, people are getting a bit more honest about 3D printing and of where the technology should be used. We've got to get away from making trinkets and toys to making real world products. I really encourage people to stop doing the trinkets and toys thing because the technology has to move out of the prototyping and into the production space.
And on the materials, are you an open platform?
Yeah, we can do either. We'll sell the powders, which people do buy to start with, but then they can choose their own powders on an ongoing basis. Typical materials that are used on our machines are the coppers and all the copper alloys. That's brasses and bronzes and those things. The aluminium's 6061. So we don't need to go to the typical laser bed materials. We can use very standard materials such as 6061, which is by far the most common machined alloy out there today. And then into the stainless steel 316. And then there's some specialised powders we work with it as well. But generally, those are the materials we're focusing on. We're not into the hard steels. There's better processes for hard steels. So really, it's those coppers, aluminiums, and stainless steels where our focus is.
Sure. And certainly it's been an interesting year based on the pandemic, but I guess looking 6 months to a year out, what are you excited about related to your company, your industry, your potential projects you have coming up?
For us, it's all around defence. The defence sector is really, really hotting up for us at the moment, and getting more and more expeditionary printers out there. So showing to the world and to defence forces wherever they are that people can control their own supply chain, because in the defence, the other important thing about 3D printing and specifically for defence is sovereign capability. So you must be able to control your own destiny, and being able to build your own parts on the front line wherever you are is such an important criteria for the ongoing support of defence worldwide. So we see this space in particular as key, especially over the next 12 months. The commercial world is reeling somewhat, let's call it, from the pandemic, but the defence sector is counter-cyclical. They're really ramping up their interest in this technology and what we can do. And that's, everything from Army, Navy, Special Forces, and similar groups.
Byron, well, thank you so much. I've really learned a lot about SPEE3D. And if companies or if organizations, individuals are interested in learning more, where would you point them?
Yeah, just jump on our website, SPEE3D.com, and drop us an email through there, and we can point you to the correct people.
Fantastic. Well, thank you so much for your time.
Great. Thanks, Mike.